Custom-developed applications constantly interact with sensitive user data and the open internet. This continuous exposure presents a uniquely large risk surface for an organization. Many security professionals enter the field with a system administration background. This operational history often creates a bias toward perimeter defenses, like configuring firewalls, over investigating code-level vulnerabilities. A perfectly configured network perimeter provides zero protection if the application running inside it is architecturally flawed. Every software project is bound by a single, unavoidable constraint: the security trade-off. This diagram illustrates the tension, balancing security, functionality, and user-friendliness. Dialing up security demands sacrifices elsewhere, raising costs, adding overhead, and reducing throughput. Because of these costs, security controls must be engineered early in the software development lifecycle, when conceptual definitions are established. To understand where an application is vulnerable, we evaluate its architecture across three specific tiers: the execution layer, the component layer, and the runtime layer. Securing software requires making deliberate architectural compromises at every stage of development, long before a network perimeter exists. At the hardware level, central processing units only read binary machine code. Developers rely on high-level programming languages to translate complex logic into instructions. The first major architectural choice is how that translation happens, dividing languages into two distinct categories: compiled and interpreted. With a compiled language, developers feed source code through a compiler, outputting a locked binary. This binary resists end-user manipulation, but a malicious programmer can hide an undetected backdoor. The primary threat is reverse engineering, using decompilers to convert the executable back into readable code. To counter this, developers apply code obfuscation techniques, scrambling the executable's logic to impede reverse engineering. Interpreted languages take the opposite approach. Raw source code is distributed directly to the user's machine. This transparency stops the original developer from hiding malicious logic, but anyone who touches the downstream file can read, modify, and embed exploits. Furthermore, some languages rely on intermediary runtime environments, like the Java virtual machine, which introduce entirely separate execution vulnerabilities. The language choice dictates an organization's risk profile, determining whether threats originate internally from their developers or externally from downstream tampering. Moving up the stack, modern applications are rarely written entirely from scratch. Developers rely on shared software libraries, importing pre-written code to handle common functions. Incorporating external open-source code means importing external vulnerabilities. A flaw in a single shared dependency immediately compromises every application that relies on it. The Heartbleed vulnerability in the OpenSSL library demonstrated exactly how damaging this supply chain failure can be, forcing administrators worldwide to patch thousands of systems. Beyond external dependencies, internal architecture is typically structured using object-oriented programming, or OOP. OOP isolates specific functions into discrete objects. This provides a black box security benefit, encapsulating the inner workings and restricting access to tightly controlled inputs. The stability of OOP architecture relies on cohesion and coupling. High cohesion is the optimal state where internal methods within an object serve a tightly related purpose. Low coupling is the optimal state where objects operate independently, requiring minimal interaction. Maintaining low coupling restricts the propagation of errors. If an attacker finds a vulnerability in one isolated object, they cannot easily leverage it. A secure component layer demands constant vigilance over external libraries and rigid, independent isolation of internal objects. Once execution and component layers are built, the software enters the runtime layer. This live environment is where applications interact with unpredictable human users. User input is the primary vector for application attacks. Providing values outside expected parameters can immediately trigger a failure or open an exploit. To stop this, developers use input validation. The absolute rule is that validation must occur on the server side to prevent manipulation by local browsers. Unvalidated input allows attackers to execute unauthorized commands via HTML injection. The server prevents this with a limit check, verifying input matches expected data types. It also neutralizes attacks by escaping input, transforming risky brackets into safe character strings.
Despite perfect input validation and rigorous object-oriented architecture, an application will eventually encounter an unexpected condition and system crash. When this happens, developers must have pre-planned a binary architectural response. The system must either fail secure or fail open. A fail secure state prevents unauthorized access by sacrificing system availability. The Windows blue screen of death is the perfect example. To stop an application from gaining direct hardware access or interfering with memory, the operating system intentionally halts all operations entirely. A truly secure application dictates the exact terms of its own death, ensuring data remains protected even during a total system catastrophe. Managing these specific technical details requires moving past the runtime environment and viewing the software through the lens of project management. When an application fails, developers face a diagnostic dilemma known as error handling.
Programmers rely on detailed error messages to debug code and diagnose user problems. However, exposing that granular data publicly creates a significant security risk. Public debugging modes reveal the underlying structure of database tables and internal server addresses. These must be disabled entirely on any externally accessible server. Instead of displaying system exceptions to the user, the application must route detailed logs of authentication failures, access control drops, and tampered data to a centralized secure repository. These logging requirements, alongside fail-secure states and input validation parameters, must be formalized during the conceptual definition phase of the software lifecycle. We have evaluated software architecture across 3 tiers: language execution, component abstraction, and runtime resilience. This brings us back to the foundational constraint governing the entire process. Securing each of those layers required an explicit cost. Whether implementing code obfuscation, enforcing low coupling, or dropping into a fail-secure state, the application sacrificed either ease of use or throughput. Secure software development begins with an uncompromising architectural commitment, established long before the first line of code is ever written.